we're recording. Okay. So where were we? Well, let's pull this up. Okay, so yeah, we had just introduced the Einstein model of solid, okay? And so the third problem on the quiz today was kind of talking about that a little bit. So in general, when we're talking about Einstein solids in StatMech in this class, they're always going to be in 3 dimensions because those are the only 3 spatial dimensions that we can actually observe. So every single particle is going to have one oscillator corresponding to every single dimension or direction. So for a 3-dimensional solid, if you have n oscillators, we'll usually refer to a solid in terms of its number of oscillators, then it has n over 3 particles because every single particle has 3 oscillators, okay? So this is just a review from last time. So yeah, we started with n equals 3, so that's 3 oscillators. So the way you can picture that, of course, is every single oscillator has this kind of quadratic potential. The energy levels are equally spaced as so. Because of quantum mechanics, you only have discrete energies in units of h times f, where h is the Planck constant and f is the frequency. And we were just doing some like by hand multiplicity counting before. So we were saying that if you want to look at the multiplicity function for the macro state where the energy is 0, then there's only one way to do that. You can only put all these oscillators into their bottom energy state. I said before that technically this isn't E equals 0, it's E equals 1/2 h bar omega, but we're just going to call the state E equals 0. Okay, so just in case that bothers anybody. So then counting the next state, so the next macro state would just be an energy of 1 unit. So now we've got 1 unit of energy to distribute amongst these 3 oscillators right here. We could put it in this one, we could put it in that one, we could put it in that one, so there's 3 different ways. Let's see, I see a chat. Is Kenny recording? Yes, he is recording. Thank you, Jacob. Thank you, thank you. I swear I'm going to be better about this. Okay. So yeah, now we've got 2 units of energy to distribute. So we could put 2 in there, we could put 2 in there, 2 in there, 1 in there, 1 in there, 1 in there, 1 in there, blah, 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 6 ways. Do the same kind of counting again. You have 3 units of energy there, 10 ways. So it turns out, and we're not really necessarily proving this here or anything, we're just kind of stating a result, but that in general for n oscillators and q units of energy, you can write the multiplicity function like this, okay? So this is going to count how many multiplicity there are corresponding to the macro state where there are n oscillators and q units of energy to distribute. And we talked a little bit about how you should think about this binomial coefficient. Wrote a little bit about that down here before. Just in general, think about this as saying n choose k, which just means that you have a set of n. You have, for example, 3 choose 2. You have a set of 3. How many different ways can you choose 2 of those 3 things? And so I went through here exactly how you can do that. Well, if you do 1, 2, 3, you can choose 2 that way, you can choose 2 that way, or you can choose 2 that way. And so there are 3 different ways to do that, which lines up with the definition presented up here. Or, yeah. Okie doke. So, moving on. Okay, so the notation that we're going to use here is going to be the following. So the way we're going to divide this up in general is we're going to do it like this. I'll describe it in just a second. Oop. All right, so what the heck am I drawing here? Well, what this picture is meant to represent is 1, 2, 3, 4 oscillators and 1, 2, 3, 4, 5, 6, 7, 8 units of energy. So this is going to help us in kind of proving why that multiplicity function is what it is, okay? Just thinking about it in this way. So think about these bars here as dividing the different systems. So like this is one system, this is the second system, this is the third system, this is the fourth system, and then however many dots are within those systems is how many energy units is allocated into that specific system or oscillator. So like the first oscillator has 1, the second has 3, third has 0, and the fourth has 4. Okay, so what we need to notice now is that in here, every single possible arrangement of these lines and dots specifies a valid microstate. So every possible of lines and dots specifies okay. So you can rearrange these however you like, and it'll always tell you a possible arrangement that corresponds to an actual microstate. So hopefully that's easy to see. I mean, you just shuffle the symbols around and it means the same thing, but it's a different microstate. So what we need to notice here is that there are q dots plus n minus 1 bars. So this is the total number of symbols that we have available to us. And what we want to do, the mathematical expression for the number of ways to arrange this, is we want to choose q of them. So we have q energy units, q of them to be dots. So that's just how we would say in words exactly what we want to do to count the number of possible configurations corresponding to this. Well, we have a mathematical device that we know kind of corresponds to this language. So if you have this blank number of things and you want to choose blank of them to be whatever, that's just going to correspond to the binomial coefficient. And so now you see, hopefully, why it makes sense that sigma of n and q is equal to the binomial coefficient corresponding to q plus n minus 1, and then q. Because this is the number of symbols that you have, and this is the number that you want to choose. Okay, so that just corresponds to what we just said here before. So notice that this is substantially different than the multiplicity that we had before for the two-state system. Which looked like this, and we just talked about earlier in the quiz. So it looked like you've got a total number of n, there where we were talking about coins. You choose n of them with an arrow to be heads up. That multiplicity function looks like the following. Oh, that's not an arrow. Boop. Okay, so yeah, these two things are very different, obviously. So don't ever get them confused. All right, so now that we've kind of introduced how you can count the microstates for an Einstein solid, we're going to move ahead to an interacting system of Einstein solids. So we know how to count for 1. Now let's consider a system of 2. So let's think about it this way. We've got some solid we'll draw as a block, another solid, and we refer to these as being weakly coupled. So this whole dotted line here just encapsulates the whole system. And so weakly coupled here is just going to mean that they exchange energy much more slowly than the intersolid exchange. So over short times, then the energies are roughly constant. So over short times, UA and UB are roughly constant. Over long times, they will equilibrate, though. So now if we want to specify a macro state, we need to specify what? We need to specify UA, and that also will specify what UB is. I see a chat. Oh, that's from a while ago. But on long time scales, these two systems right here will exchange energy. So the only thing that's actually being specified by UA and UB is the sum of them, right? So on long scales, UA and UB, they fluctuate. So then only thing that matters, or the only actual variable corresponding to the microstate is specified by UA plus UB, because obviously the total energy is conserved. Okay. Now let's consider the specific system. Na equals Nb equals 3. So the number of oscillators in each is just 3. So it's one particle, basically. So consider the specific. So the first Einstein solid is equal to the second Einstein solid in terms of its number of oscillators. And they each have 3 oscillators. So one particle each. And we'll say that Q total, the total number of energy units that we have to distribute, obviously that's equal to QA plus QB, and Q is always going to be related to the actual energy itself. Here Q is just the number of units that we think of as being able to distribute. So we're going to specify this to be 6 for right now. And maybe I should have written that on the next page, but I'll just write it again, I guess. NA equals NB equals 3, Q total equals 6. Okay, so we could ask ourselves, how many macrostates are there? Well, macrostate is just going to be specified by saying how much energy is in one of them, right? Because then since we know the total amount of energy, that automatically specifies the amount of energy in the other one. So we'll just refer to the macro state by specifying what QA is. Okay, so, well, we could have QA be 0, we could have it be 1, ... all the way up to it having all of the energy units, 6. So then there are 7 macro states. And here we could also just write QB. It's automatically specified by QA since they're bound by the total. So it's just 6 minus QA. And then just keep on subtracting ... all the way down. So for each macro state, we can use the binomial coefficient to calculate the microstate multiplicities omega A and omega B. So can use omega A and omega B, just the multiplicity corresponding to A and the corresponding multiplicity for B. So then, if we want to calculate the total multiplicity, we can just take the respective ones and multiply them together, right? So at this point, we're going to kind of move into showing what happens when these systems get really big. But I wanted to first show you a little Mathematica animation that I made up that displays this pretty nicely. So give me a moment to bring that up. Oh, where did I put it? Einstein solid. Go. Programming, just let me know. But it sounded like most people were familiar with some kind of programming language. Okay, doke. So where were we? Oh, yes. Okay, so we were just gonna, we had our system of uh, two Einstein solids, one with 3 oscillators, the other with 3, and then a total of 6. So the last thing I wanted to calculate here was the total number of microstates that available over a large amount of time. So you would just take 6 plus 6 minus 1 and 6. So taking all of our energy units and throwing them in there. Then this, if we calculate all the factorials, would be 462 total microstates corresponding to the system. I should have done this before I went to the Mathematica, so sorry about that weird interruption. So this is the total number of accessible microstates from the system right here. And the way you're doing that is just you're taking these two and multiplying them together. Okie doke. So let's just make clear exactly what our assumptions are here. So our assumptions are that over large times, the energy moves randomly. The energy in the system, it moves about randomly, such that all microstates are equally probable. And so this is what's known as the fundamental assumption of statistical mechanics. And so it's just saying that, like in that animation that I was just showing you before, every single one of those dots along the x-axis, they're all technically equally probable. So they all contribute the same amount of weight to the probability. So literally what's going on here is that whichever macro state has the most number of microstates is the most probable in the straightforward way. So where was I? Okay, so from our example before, if we take this assumption, then we have that all 462 microstates that we had just calculated are equally probable. This is our fundamental assumption. So like I literally just said, the macro state probabilities are proportional to the relative number of possible microstates. Okay, so for example, if we want to calculate the probability of QA equal to 1. So in our system before, we had two Einstein solids. If we want to find the probability for a macro state where the first Einstein solid only has one unit of energy, then this would be 63 over 462. So we had calculated what the total number of microstates available was. And now we're just using the same multiplicity formula to calculate what the multiplicity is specifically for QA equal to 1. That ends up being 63. So this is roughly a probability of 0.136. Now if we look at another, let's say QA equals 3, this one ends up to be 100 over 462, which is roughly 0.216. So at least for the scales that we're looking at right now, the point is that these aren't very different. I mean, obviously this one is bigger, but it's not that much different than 0.1. Like 0.2 and 0.1 are pretty close. But the whole idea of statistical mechanics applied to large systems is that as the number of particles or oscillators or whatever, the number of oscillators we'll say here, as that increases, these two get wildly different from each other. So the state where the energy is dispersed evenly amongst the system, we'll see, is incredibly, incredibly more probable than this one. So as the number of oscillators increases, this changes dramatically. Alrighty. So let's just kind of display this. So if we took NA to be 300 now rather than 3, NB to be 200 rather than 3, and Q total to be equal to 100 units, and we were to calculate, even though we're not going to do it right here because these numbers are absolutely insane, if we were to calculate the number of microstates corresponding to the least likely state, that would be a number that looks like 3 times 10 to the 81. So if we were to calculate this, the number of microstates corresponding to the macro state that ends up being least likely is 3 times 10 to the 81. You would say, oh, that's a huge number. Like, I don't see what you're talking about. Well, let's calculate, or let's just see what omega is for the most likely. this ends up being something that is like 7 times 10 to the 114. So there's like a order of difference here of like 10 to the 33, right? That is incredible. Like that's a huge, 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 huge number. So for all intents and purposes, I mean, this state, the one that's most likely, it's the only realistic state. I mean, this one's not even close. If you're talking 10 to 33, that's just absolutely insane. So as I was trying to show before on the animation, what happens is that you go from a plot where here we'll write like omega total QA, you go from a plot that looks something like this at like small systems with small amounts of energy. It goes from something like this where everything looks kind of on the same footing, and then you increase it just to something that's on the order of 300. It goes to something that looks almost like this. It's just like a spike, and then everything else is just completely washed out. So that's really the idea that we're trying to get across right here and now, okay? Is that when you have big systems, really the most likely state is like the only possible accessible state. So, knowing this now, what can we say? So we can say if the system starts somewhere in like the least likely state, in a lower p state, and you wait a long period of time, you can pretty much guarantee that it is going to be in somewhere in this area after a long period of time. So after a long time, it will certainly have moved to the most So if you started off somewhere where it's not in equilibrium, it's somewhere out here, you wait some long time, you can almost guarantee, since this state is so much more probable, it's going to wind up in that area. Okay? Yeah, yeah. Mm-hmm. Yeah. Yeah, that was potentially confusing because of the order that I did it. So sorry about that. The only thing I was increasing in that animation was the total number of energy units, because I didn't want to spend a lot of time and make a couple different animations where I increased this, and this all at the same time. But really, in your homework assignment, you should just increase all of these like proportionally. But like even if you only increase one of them, you still see this feature. As the system gets bigger, as you have more microstates that are available overall, you do see this peak feature regardless of which of these you're increasing. But yeah, in the animation, I was only increasing the energy. Let's see. I'm just reading a chat real quick. I hope that answered your question. Okay. All right, so this idea right here. Yeah, yeah, yeah. Go ahead. Mm-hmm. The second most likely? So the second most likely, it'll lie like somewhere in here. So, I mean, I can't give you like an exact number right off the top of my head, but just know that like qualitatively, like the difference between like this state right here and this state right here, like while it is like half as probable, this one is still like so much more probable than anything out here. So for all intents and purposes, you can just treat everything in the zone as being equally probable. kind of, is how I would think about it. Does that make any sense? Or you were looking for like a specific number? Mm-hmm. Yeah, yeah. Yeah, well, it's not going to be as great of a difference. So I guess what we're not necessarily saying is that you'll be in only this state right here, like literally the most likely, but that you can guarantee that you'll be in this very small zone right here. I mean, you will end up seeing like small variations around here because these are all like roughly in the same ballpark. But yeah, I mean, just because you start out here doesn't mean you will find it literally right there. There will be some plus or minus. Um, which yeah, does that help at all? Okay, cool, cool. Um, yeah, yeah, yeah. Right. Yeah, yeah, it doesn't. It doesn't. So the time evolution that I'm doing here is really wonky. It's I drew this plot, and then sometime after that I drew this plot. So that's your time evolution. So I mean, there's no real time axis here. Um, it's just that so the way you want to imagine this is that if you start off like let's say somewhere out here. Actually, what I just said was wrong. So this was corresponding to a plot for a small system with small amounts of energy. So what I'm saying now is like, let's take the big system, which corresponds to this plot, the really spiked one. Let's say you start somewhere out here. Okay. If we take that every single microstate is technically equally likely, then we can say this statement, which is that obviously like this is going to be the most probable state because there are just more of them. And the way time is moving here, what we're thinking about right now is that this is just randomly moving around. It's just things are bumping around randomly and energy is distributing itself. So yeah, I mean it's not a very precise like time evolution going on here, but you're just kind of saying that you should be able to observe this fact that if you start somewhere, you wait some time, it's going to tend toward a more probable state than a less probable state. This is literally just what you mean by irreversible processes. I don't know if that helps at all. Yeah, yeah, yeah. So this thing, it's gonna bump around, but it's gonna tend towards the most probable state because there are just more of them. So it will tend toward like any particular microstate because they're all equally probable. But since there are just so many more of these ones, it's way more likely for it to have bumped itself into this one, is what I'm saying. So, like, at some point in time, it sits out here. That's this microstate. If you take a time step, think of it as branching into any other microstate, right? Because they're all equally probable. There's some transition function that tells it it's going to go from this to another one. They're all the same, technically. But if there are so many more of these, if there are just like way, way, way more options for it to get in here, then in general, it's just going to bump itself into here, right? Does that make sense? I could maybe draw it as like, I don't know, like if it starts here and it's got to move some time step, like, and let's say like these are all your options. So just to kind of depict this, like let's say that all of these options correspond to that zone, this zone right here. Well, if all of these options are equally likely, like, and I just pick one at random, you're more often than not going to choose one that's in this zone rather than this single one out here that's less likely, right? So I hope that helps. um, this is definitely some stuff that you want to spend some time thinking about on your own as well. So what did I want to say here before maybe calling it? Oh yeah, so I wanted to say that this is kind of why, or it is why, heat flows from hot to cold. And so at this point, we kind of introduce the so-called second law of thermodynamics. Which we can at least praise in an all right fashion right now, but we'll introduce entropy a little bit later and we'll reframe it again. But basically the statement is this. In an isolated system, so meaning energy is not entering or leaving in any shape, form, no work is being done, no heat's being added, nothing's going in or out. So in an isolated system, the system inevitably moves toward the most probable states. And what we'll reframe this as later is that entropy, which is something we're not defining right at the moment, but you've probably heard this phrase before, entropy can only increase in an isolated system. That's all this is saying. Okay, so we're actually at, well, we'll get through the rest of this. Is everyone okay with going over like 15 minutes or so? Oh, so yeah, somebody is asking, how do we know that a hotter state is more probable? So yeah, I didn't explain that super well. Okay, and cool, we can go over 15 minutes or so. So a hotter state is more probable for exactly the reason that we were just saying before. So every single state is equally likely, but it just so happens that what you mean by hotter has a greater number of multiplicity corresponding to that macro state. So they're just, if you take like the air in a room, for example, well, yeah, so let's take like a box that is T1 and a box that is T2, and let's say T1 is greater than T2. So this box is hot, this box is cold. So we're trying to answer the question, which was, why is a hotter state more probable? So if you think about temperature as just being like a way to distribute the energy, so T just has more energy distributed to it in this sense right here. So the reason that heat is going to flow from T1 to T2 is because there's actually more microstates corresponding to the macro state that has energy more distributed. So there are just more states available if you have the energy distributed between the two. So since we've said that the system will move toward the most probable state, and there are more microstates corresponding to distributing the energy throughout both of these rather than just putting it in one, then that's why heat is going to flow from hot to cold. And these two systems right here will equilibrate and come to the same temperature. I hope that helps a little bit. So now we're going to do a little bit of a silly section. This is the section Schroeder calls large systems. And the stuff described here is not like a rigorous mathematical result by any means, but it's a useful way to think about stuff in StatMech, because you get really big numbers, you get small numbers, and you get insanely huge numbers. So what he says is that there's kind of like a distinction. So there's three different orders of magnitude. There are what we call small numbers, and these are things like 6, 23, 42, whatever, like just, you know, counting numbers, things that you can count and hold in your head. And there's no rigorous like delineation between this and the other sets, so don't try to ask that. This is not rigorous in any way. There are also what we'll call large numbers, which we'll say are just what you get by exponentiating small numbers. So stuff like 10 to the 23, 10 to the 42. And the property about large numbers that we'll use in StatMech is just that in general, it's a good approximation to say that a small number plus a large number, so like 42 plus 10 to the 23, is just roughly 10 to the 23, right? You can add a few to a huge number, and it doesn't really change a whole lot. So this is all we mean by large numbers. But then we also have very large numbers. And I'll put like much greater than signs in between each of these, just to denote exactly what we mean here. And so large numbers are just going to be, or very large numbers are going to be large numbers that are exponentiated. So like 10 to the 10 to the 23. And so the nice feature about very large numbers is that you can take a very large number, 10 to the 10 to the 23, and you can multiply a large number, and it doesn't change approximately. So this is 10 to the 23 plus 23. And this is just a carry forward of the approximation scheme that we used for large numbers compared to small numbers. So this is approximately just 10 to the 23. So just wanted to introduce kind of how we're going to think about 3 different orders of magnitude here, and how you can legally in StatMech like add things together and take approximations in this way. So kind of keep this in your mind whenever you're doing calculations and you have like a small number added to a large number. Well, you can just get rid of the small number. Just forget about it. It doesn't matter. Just basically the whole point of this section is just him telling you basically how to keep track of what actually matters. And then he puts out a few properties of like logs and exponentials, which I can quickly review. So recall that if you have log base 10 and you take log base 10 of 10 to the 10 to 23, all that'll do is it'll just bump you down one level. So it'll take a very large number and turn it to a large number, 10 to the 23. You could also take log base 10 of log base 10 of 10 to the 10 to the 23, and that would get you all the way down to a small number, like 23. So log is a way for bringing you down in this order of magnitude scheme. Likewise, the exponential is just going to be a way of bumping yourself up. So you could do the same kind of stuff, but with the exponential, and just show that it takes you from a small number to a large number to a very large number. And that's all I really have to say about that. So hopefully at least this wasn't confusing at all. It's just kind of getting our definitions straight and making sure that we're all on the same page when it comes to approximating numbers. Okay, so that's all I'll go through today, and I'll post